Alright, let's continue. Okay, let me open the table of content first. Okay, we are still in chapter 26 here. And now let's take a look at the homework simulation. Let me open that. Okay, there's the simulation. x86.py allow you to see how different thread interleaving either cause or avoid race condition. Okay, see the readme for details on how the program works, then answer the question below. Let me open that. x86. Think in the intro one. Okay, yeah, let me take a look at the code. Oh, 1000 line. Okay, interesting. Random set, time clock, to space. Okay, I guess we need a helper to print out the space, maybe something like that. Assert. Okay, if condition false, abort. Okay, how much memory? Okay, oh, condition register in system. Okay, using this register, I assume. Okay, use memory, trace and register to trace. I guess this is the program counter, if I remember correctly, for printable version. What's in memory? Okay, return zero value register. Register cannot be traced because it does not exist. Interesting. Init condition code. This one, I guess. Okay. Condition. Init memory. Okay. Memory term. Alright. Here I'm just taking a look at the code here. Instruction. Okay. What is a yield in here means? Okay. Save memory. M to L. I guess this means not sure about I to R, but maybe M in this case mean memory to register. But what is I? I'm not sure yet. Is it constant maybe? Or yeah, maybe value, something like that, constant value. Okay, and then from register to memory, I assume. Then register to register. Okay, and then this one add. Okay, and then soup. Alright, support for lock, atomic exchange. Okay, fetch add. Self register. Okay, this is the condition, I guess. Less than equal, something like that. Less than, not equal. This, okay. Yeah, there's a lot going on here. Call and return. Okay. I feel like this is, what is it called? Replicating the assembly instruction. I call, return, and then push here. Of course, there's also pop, right? Okay, register translate. In parsing MOV, quite primitive. Another operation. Return. Where type is okay. This is the register. This is the immediate, or some people call this constant, I guess. The immediate value. And this is direct memory. Memory plus register indirection, maybe something like that. Memory plus 2, register indirect. Oh, this one is not handled. Okay. If I understand correctly, this means that we add this with this offset and also adding this bx register multiplied by 4. If I understand correctly, this is what this syntax mean. Okay, argument, okay. Alright. So alpha is digit. Yeah, we will only take a glance, I guess. Only take a look a little bit. everything else. Okay. Main operation code, I guess. But move to memory argument. Yeah, as far as I understand, we cannot move directly between two memory here on x86 architecture. I'm not sure why, but that is the case. So we can only move from, let's say, memory to register or register to memory, but not memory to memory, if I understand correctly. Then is that. Okay, to immediate argument, yeah. I mean, if we, what is it called? If we move the two constant value, like where do we store that, right? Something like that. Okay. Oh. Yeah, I feel like this is, what is it called? Maybe replicate the assembly instruction, x86 assembly instruction. Maybe something like that. Yeah, I'm not sure what this instruction do, but I've seen that somewhere. This is test, and if I remember correctly, this is like the AND operation. So basically check with the, what is it called? The logical AND operation, maybe something like that. Unconditional jump if not equal, jump if equal, jump if less than, if I remember correctly, right? Jump less than, and then jump less than or equal, thing like that. Yeah, I'm not sure about yield or halt, or maybe no operation. But what do we do with this no operation? Increment the program counter here, print header, okay, print trace, integer run. Okay, process list. Okay, process class. And then this is the option. Oh, there's a lot of options. Like usual, there is the random seed here, number of thread, source program. Oh, interesting. assembly, right? Okay, interrupt frequency. Oh, there is assembly code here. Okay, interesting. Interrupt frequency. Default is 50. What is it called? The measurement here, 50 second or maybe 50 millisecond. Hardware in it. Okay. Yeah, what is the measurement we use here? Maybe 80 second. Maybe. I'm still not sure yet. If interrupt are random. Oh. Okay. So we can make the interrupt random or not. If the interrupt not random, is it gonna be like, for example, every 50 second here? And if it is random, maybe one interrupt, not necessarily every 50 seconds, but within the 50 second interval. I am still not sure yet. Okay, and then this is the argument. Specify multiple register per thread via column spirit list. Okay. Look like this is the argument vector for the register. Maybe something like that. Load address. Address where to load code. Okay. Size of address space. Memory trace. Okay. Default is empty. Oh. Register trace, I guess. Default is also empty. Should we test condition code? Condition code. Interesting. Print start. Print some extra stat. Okay. Some extra info. Now I wonder what is the difference between stat and info. Yeah, I'm not sure. Is the stat included in the info here? Or maybe it is a different type of information? Well, we will find that out later on, I guess. Okay. Must be one per thread or just one set of value for all thread. Okay. What is argument vector gain for multiple register per thread? Main program. Why are we assign debug to false twice? I don't understand. Isn't this gonna replace the previous one? So why is there 2 here? Nothing here. No explanation in the commit message. Okay. Load up program. Procs. Okay. Get first one ready. Run it. Alright. Start instruction. Emulation rate. Oh. So the statistic in here, maybe some kind of instruction and emulation rate. But what is the info? I don't really understand. Or maybe verbose. Okay. Oh, CPU verbose. Okay. Assign var. Okay. Alright, look like there is some difference between stat and verbose flag. Maybe verbose flag is for the, what is it called? For the operation the tile, but the stat is for the running statistic, maybe something like that. Who knows? Let's read the readme first. Okay, welcome to this simulator. The idea is to gain familiarity with threads by seeing how they interleave. The simulator x86.py will help you in gaining this understanding. Familiarity with threads by seeing how they interleave. Okay. The simulator mimics the execution of short assembly sequence by multiple threads. Note that the operating system code that would run, for example, to perform a context switch, is not shown. Okay. Tools are used is the interleaving of the user code. I'm kind of curious what interleave mean. Okay. Alright. Interleave of the user code. The assembly code that is run is based on x86 but somewhat simplified. In this instruction set, there are 4 general purpose registers: AX, BX, CX, and TX, a program counter, right, PC, not personal computer, and a small set of instructions which will be enough for our purpose. Here is an example code snippet that we will be able to run. I assume this is the label, maybe something like that. But why there is no colon? I don't know. So yeah, maybe this is the label, but I might be wrong. Get the value at the address, this one, the 2000 address, and then moving that value into the AX register, and then increment it by 1, the immediate value or the constant value, I guess. And then what is it called? Basically add 1 to the value in the AX register and then putting the result in the AX register, if I understand correctly. And then we move back the value from the register to the previous memory address. Store it back, right? And then halt. Oh, okay, interesting. The code is easy to understand. The first instruction, an x86 MOV, simply loads a value from the address specified by 2000, right, into the register AX. The register AX, addresses in the subset of x86 can take some of the following form. 2000, the number 2000 is the address, and then this, what is it called? Bracket, register name here, contents of register in parentheses from the address, okay, and then this one, the immediate, if I remember correctly, the immediate, and then the bracket with register name inside of it, the number plus content of the register from the address, okay, and then this is the immediate, and then with to register inside of the parentheses, the number plus register 1 plus register 2 from the address. I think, if I remember correctly, some people say this is something like the reference, a pointer. So basically the value of this register is the address, so that's why we need to put what is it called, to put the bracket to get the value from this address. But again, I might be wrong, so that is what I learned, that this kind of syntax similar to the dereference pointer in C, but I'm not sure how true is that yet. Okay, to store a value, the same. MOV instruction is used, but this time with the argument reverse. Right, this one. The add instruction from the sequence above should be clear. It adds an immediate value, or the constant value, I guess, specified by $1 to the register specified in the second argument. Basically something like this, right? We add the content in the register AX with 1 and then putting the result back into the register AX. Thus we now can understand the code sequence above. It loads value at address 2000, adds 1 to it, and then store the value back into address 2000. The fake is halt instruction just stop running this thread. Let's run the simulator and see how this all works. Assume the above code sequence is in the file simple res.s. Okay, something like this. We provide the program name with the test_p flag here, and also test_t. What is test_t? Thread. Oh, number of thread. The number of thread is only 1. Okay. Thread 0. Okay. The argument used here specified the program test_p, the number of thread, right? And the interrupt interval. Oh. And the interrupt interval width is how often a scheduler will be woken and run to switch to a different task. Because there is only one thread in this example, this interval does not matter. Wait, what? Where is the interval? Is it the default value here? Interrupt interval? Maybe this one? Maybe. I mean, we didn't provide, what is it called? We didn't provide that in the command line argument here. So maybe for the interrupt interval here we use the default one, which is 50 seconds maybe. It is how often a scheduler will be woken and run to switch to a different task. Because there is only one thread in this example, this interval does not matter. The output is easy to read. The simulator prints the program counter, here shown from 1000 to 1003, and the instruction that gets executed. Note that we assume unrealistically. Okay. This is important, unrealistically. All instructions just take up a single byte in memory. Oh. Okay, yeah, we assume that all instructions only use 1 byte in memory. Okay, that is the unrealistic part, I guess. That all instructions take up a single byte in memory. In x86 architecture, instructions are variable size and would take up from 1 to a small number of bytes. We can use more detailed tracing to get a better sense of how machine state change during the execution. And use more detailed tracing to get a better sense of how machine state change during the execution. What is this uppercase M here? Let's take a look. I mean, there is this lowercase m, right? And there's also this uppercase m. Address to trace. Oh, okay. This is address to trace. Where do we get this trace? Oh, from this one. Okay. Alright. And then what is uppercase R or R? The register to trace. Okay, AX and PX. It is, well, AX is this one, right? The register that we use in the instruction. But why PX2? Oops, forgot the DESI flag to compute the answer, right? Okay. Oh, maybe PX is just for the comparison here. That the register PX still empty or something like that. Okay. So we have value 0 in the address 2000. Maybe something like that, right? Again, this one. And then we move value 0 to register AX and then adding 1 in the register AX. And then move this one value from register AX to address 2000 here, and then hold. By using this M flag, we can trace memory location. A comma spared list lets you trace more than one. By using this R flag, we can track the values inside specific register. The values on the left show the memory or register content after the instruction on the right is executed. Right, so after the instruction has been executed. So for example, this one, the one on the left here is the result when this instruction execute, or maybe this one, the, what is it called? The easiest example, I guess. So after we execute this instruction, the state of register A changes to 1. Something like that. That's why this is the content after the instruction, right, on the left side. For example, after the add instruction, you can see that register AX, I keep saying this AAX, the 32-bit variant of the, what is it called, x86, right? And I don't remember which bit this is. Maybe 8-bit register, or maybe 16. Yeah, probably 16, but I'm not sure yet. see that AX has been incremented to the value 1 after the second move command here. Instruction add program counter 1002, this one, right? You can see that the memory contents at 2000 are now also increment. This one. Right after we execute this is the state of memory address 2000. The value in the memory address 2000, maybe something like that. There are a few more instructions you'll need to know, so let's get to them now. Here is a code snippet of a loop. Oh, there's main and top. Interesting. Okay. So we subtract 1 from TX. Okay, and then putting the result in the TX register. And then check whether TX 0 or not. I assume this is what it means. And then if TX equals 0, okay, I mean this instruction should be jump if greater than or equal. So if TX more than or equal 0, we should go to the top level here. Maybe something like that. So I feel like this is some kind of looping. So we iterate the instruction until the condition is false, until TX less than 0, maybe something like that, from the subtraction instruction. And then after that we halt. So if the content in the TX register less than 0, we execute this halt. Okay, a few things have been introduced here. First is the test instruction. This instruction takes 2 arguments and compares them. It then set implicit condition code, right? The flag, what is it? The register flag, maybe something like that. Kind of like 1-bit register, which subsequent instruction can act upon, right? So after we change the flag in the register flag or R flag, I guess, in the 64-bit system. But yeah, after we set those flags, we can use this jump conditional instruction to check the value, the condition value, and then jump if it is correct and ignore this if it is incorrect, something like that. In this case, new instruction is the jump instruction. In this case, GTA, jump greater than equal, which stands for jump if greater than equal to this instruction jump if the second value is greater than or equal to the first in the test. Right. So if the TX is greater or equal than 0, if I understand correctly. Okay, one last point to really make this code work. Tx must be initialized to 1 or greater, right? Thus we run the program like this. Oh, okay. So we can initialize the register with -a flag here. Okay. That is why we need this. Okay. Oh, this is per thread, I assume. Okay. Thread 2. Oh, colon spirit. Okay. If we use comma, the argument is per thread, like this one. This is thread 1, AX. What is it called? The initial value for AX register is 1, and then thread 2, the initial value AX is 2. But in this case, using the comma, not comma, the colon, I guess. Using the colon, we, what is it called? We specify multiple initial value for the register in one thread. So this one, AX and BX, is for thread 1. Something like that. Okay. And then I guess we trace the TX here. What is uppercase C again? We trace condition code. Oh, okay, interesting. And then compute. Alright. Oh, now this is interesting. This is the condition code. Okay. The tests are TX flag trace the value of TX register. The TC flag trace the value of the condition code that gets set by the test instruction. Okay. Trace the value of condition code that gets set by a test instruction. Okay. Finally, the test A TX equal 3 flag set the TX register to the value 3 to start with. As you can see from the trace, the sub instruction slowly lowered the value of a TX the first few times test is called. Only the what is it called? More than or equal and more than and not equal condition gets set. However, the last test in the trace find TX and 0 to be equal, and thus the subsequent jump does not take place, and the program finally halt. Okay, TX and 0 to be equal. TX and 0 to be equal. Wait a minute. Okay. I assume this is the result. after this one, maybe jump greater than or equal, right? Or maybe this is the condition before we run this. Maybe, but interestingly, this is the condition after we run this. Okay. Yeah, that is interesting and kind of confusing, I guess. But from this we can know that the flag here will not change before we execute this instruction, and then this will change after we execute this instruction, right? And then we test that, and it turns out this flag is what is it called? Set. This flag is set, right? The less than, and also the less than and equal, I guess. But more importantly, the less than, because the equal is part in this instruction, greater than or equal. So we check for the less than, but not equal. The flag is set in here, and because it is set, we skip this instruction, the GKDA, the jump if greater than or equal, and then we halt. But I'm not sure about this explanation. The last test in the trace find dx and 0 to be equal. It is not equal, right? But less than. Find that dx less than 0. And thus the subsequent jump does not take place, and the program finally halts. At least from what I understand, it is not equal. To make the subsequent jump not take place. Okay, now finally we get a more interesting case that is a race condition with multiple threads. Okay, let's look at the code first. Okay, critical section. Get the value at the address. Okay. Command install it back. See if we are still looping. Okay. Now we use greater than without the equal condition. The code has critical section which load the value of a variable at address 2000, then adds 1 to the value, then store it back. The code after just decrement a loop counter in the px register, test if it is greater than or equal to 0. If so, jump back to the top to the critical section again. Something like this, I guess. Oh, previously we only used one thread, right? This one. Now we use two thread here, thread 0 and thread 1. Okay. This is memory to trace, if I remember correctly, the mem trace, right? Okay, initialize the register value, hard switch. Okay, no lock. Alright, wait, is the okay, looks like this instruction is in the repository too. The hard switch line is insert whenever a thread halt and another thread must be run. Okay, to see something in account of two there. You know what? Let's take a look at this race condition on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.